Okay, number six. Here's a question about triple integrals in spherical coordinates. Right, so you are supposed to write an expression, a triple integral that represents a volume of a sphere of radius 5. Right? This shouldn't be a hard one. Basically, you realize that because it's spherical, the integral has to end in d rho d phi d theta. Okay, and in addition, you know what has to have what you have to have before that, right? That's the one that you sort of sing with the rhythm. Okay, it's rho square sine phi, and then the rho, the phi, the theta, right? So this part is called dv, and you should know that by heart. Okay, that. All right, and so dv includes rho square. Okay, it is a part of that thing called dv, the volume differential in spherical coordinates, and everything else is pretty straightforward. You know, theta goes from 0 to 2 pi, so that you can go all the way around, and then phi goes from 0 to pi. Remember, phi never goes beyond pi, okay? Because when phi is equal to 0, that is the north pole, and when it goes to pi, it's the south pole. You can't really go any further than that. And then rho goes from 0 to 6 because it's a sphere, right? So that's pretty simple. And it should be simple because spherical coordinates are invented to describe something spherical. Cylindrical coordinates is not as simple, but it's not too bad, right? So you have to write the equation of the sphere, and x squared plus y squared is of course r squared. You solve this for z because you know that this is your dv, the volume differential in cylindrical coordinates is r dz dr d theta. Sometimes, depending on which book you read, this is actually comes right before this. I don't like it because I think dz dr d theta should all be at the end. It doesn't matter though. Okay, but I do have to have d here. All right. Okay, so what can we say here? Theta again goes from 0 to 2 pi. That's easy. And then how about r? Well, if you see, the thing is, if you look at this whole thing, remember cylindrical coordinates are basically polar plus z, right? So you have to sort of look at this from the top. And if you look at the sphere from the top, project the whole thing to the from the top view, it's going to look like this. Okay, and so it does. The theta goes from 0 to 2 theta, and r goes from 0 to 6. That's okay. And then for each point, now you are thinking z goes from this point to this point, okay, whatever those points are. And the z values of the lower and upper bounds of z values are, of course, described here. And so that's what goes in here. All right, no problem here. Right? Okay, let's go to number 7. E is the solid bounded by the circular paraboloid. Can you tell this is a paraboloid? Yeah, because z is not squared. So maybe you may think this looks like an ellipsoid, but it's not because there is no square here. I am going to undo that. Okay, and then and the xy plane. So maybe you want to draw this. You solve this for z, and that's 9 minus r squared. And so the graph or the picture looks like this. And at this point, you can immediately think of 3 as the bounds for r, right? Because when you have 3 squared, that's 9. And so this is it. You should be able to draw this rather quickly by looking at this because, I mean, you spend a lot of time drawing those quadratic surfaces. All right, write a triple integral in cylindrical coordinates that represents the volume of this solid. All right, and you are given that it's bounded below by the xy plane. So z starts at 0. Okay, so theta clearly goes from 0 to 2 pi. That's easy. R goes from 0 to 3. That's easy. Again, because if you look at this from the top, it's just going to be the circle of radius 3. Z is not that bad either because for each R and theta you pick, Z goes from 0 to whenever it hits the surface, whose height is 9 minus R squared. So that's your upper bound. And this is your dV. Okay, so this is pretty simple. Now you can, of course, write this as a polar double integral. All you have to do is I mean, this is what you have, right? Because if you think of this as a solid above the xy plane, this will be your height. And, the double integrals are supposed to give you the volume of the, the solid under this function, which is 9 minus r squared. And of course, this is exactly what you get after the first step of evaluating this integral. Okay, if you integrate this with respect to z, then you will get exactly this. Number 8, describing in your own words what type of solid E is, what type of solid E is. If the volume of E is expressed by this, okay, another Jeopardy-like question. Oh yeah, but look at this one. It's a little different because it's written in an unconventional order. I have to confess, I got this from a calculus book, an old calculus book or something. And it's very rare for you to see any order like this, d rho, d theta, d phi. Most books will always stick to d rho, d phi, d theta, but it doesn't really matter if these are constants, okay? So phi goes from pi over 2 to pi. That's kind of unusual, right? Now, I hope you realize that this represents the lower hemisphere, okay? Why? Well, because phi is 0 up this way, right? And then phi is the angle from the positive z-axis going in all kinds of directions here. And so when phi is pi over 2, that's the xy plane. And then when you go to phi is equal to pi, that is the south pole or the negative z-axis. So this tells you, okay, this tells you it's a lower hemisphere or bottom half. Okay, and then theta goes from 0 to 2 pi. That's usual, and that means it's the entire circle. And then rho goes from 2 to 3, not 0 to 3. And so it's a sort of a hollow sphere or hemisphere, or you would describe this as the hemisphere where the middle hemisphere of radius 2 is being grilled out of the lower hemisphere of radius 3. Okay, and I mean, this is inspired by, of course, the Halloween season. All right, so the bottom half of the pumpkin of radius 3. That's why I drew this in orange. Okay, in fact, this is something you see in grocery store now. Okay, you probably didn't realize this describes something seen in grocery stores in around the end of October. All right, so this is the like the bottom half of the pumpkin of radius 3, from which the interior sphere of radius 2 has been drilled out. All right, the final question is number 9. I hope you like this picture. I actually took this a few years ago because I was thinking of calculus, and I mean, what else do you think of in your kitchen, right? And you say, whoa, this looks so cool. All right, so what is that? Set up a triple integral in cylindrical coordinates, which expresses the volume of a circular cylinder. All right, so the circular cylinder x squared plus y squared is equal to 1. That's this and this whole thing. And this is a infinitely tall cylinder, right? Sort of like a bamboo of radius 1. And now you're going to slice it. You're going to cut it by the horizontal plane. Z is equal to 0. That's easy. That's your xy plane. And then this is the tricky part of this question, maybe the only hard part of this question. Z is 2 minus x. And I hope you can see that Z is 2 minus x is this purple thing I drew. Okay, y is not there, which means it extends in the y direction, right? All that. Okay, and so if you slice it, of course, you can imagine and visualize the picture is going to look exactly like this chopped cucumber. All right, and that's why I drew this in blue, the green also. So you have to describe this. Z is equal to 2 minus x. And how do I know, by the way, this looks like this? Well, this is x plus z is equal to 2. So you know that 0, 2 and 2, 0 are the intercepts on the z-axis and the x-axis, respectively. All right, and so that's something that you should keep in mind. Actually, yeah, I'm sorry, that's not this point. This is the point. Okay, so this is 0, 0, 2, and this is 2, 0, 0. These are the points. And because this circle goes to, where x is negative 1, so this point, sorry, what is that? It is up above this. This picture is, yeah, so this point should be 3. Okay, so the height goes from 1 to 2 to 3. That would be the z value. And so that is actually, yeah, I think maybe this picture is not so accurate here. I think it should, this is the point. So this should be about more like this. All right, so yeah, okay. So this point is 0, 0. No, this point is -1, 0, 3. Okay, so that's this point, okay? This point is -1, 0, 3. And this point is 1, 0, 1. Okay, you notice here x plus z is 2 in both of these, right? All right, so that's what you have. And basically all you have to do is to write your bounds for r, z, r, and theta, right? Theta goes from 0 to 2 pi, because if you look at this from the top, it's basically the circle of radius 1. So r is also from 0 to 1. And then what's z? Well, z goes from 0 to wherever it hits this surface, the plane. And the plane is z is equal to 2 minus x, except you can't say x in this world of cylindrical coordinates, okay? X is a bad word in cylindrical coordinates. In fact, it's meaningless. People don't even know what x is. So you have to speak their language in the world where they speak, cylindrical. I don't know what kind of language it is. Probably well-rounded. And then, so what is x? Yeah, x translated in this language is r cosine theta. So z is 2 minus r cosine theta. And that's what you will have to have here as the upper bound. All right, and you can go ahead and evaluate this. Right? And this is actually good, because if you evaluate this, it's not hard to evaluate it. You get 2 pi, and it should make sense. Maybe you can see why try to figure out why the volume of this is 2 pi. Okay, think of another piece of this, just like this, a congruent cucumber piece. If you have 2 of these, okay, you can put this and another one like this upside down together, okay, and it'll be a cylinder, okay, and it's going to be a cylinder of radius. Well, radius is 1, and the height is going to be, what do you think? Yeah, height is going to be 2. No, 4. The height is going to be 4 if you combine these, right? And so the volume of this whole thing is going to be 4 pi. This is half of it. So the answer should be 2 pi, and that is what you will get if you integrate this. And that is the end of our review of triple integrals. Okay, so as I said in the beginning, this is what I would typically do in the last class period when we cover chapter 5, right? And then I'll tell my students to go ahead and look at practice test number 4 and look at the answer key. And I will be providing a video key for practice test 4 as well. So make sure you do this thing, the integral review and practice test number 4 before you take your test number 4. All right, I hope you do well, and I hope you study hard so you can learn these things well. Okay, take care. Bye.